short today too, so hopefully we'll have some time to work in class. So rational function is a question of two polynomials. We talked about that yesterday. So in a rational function, you've got f of x and g of x, where those are both polynomials. Since we are dividing by a polynomial, rational functions have restrictions on their domain. We know that we cannot divide by 0, so we must consider any values where g of x equals 0 and restrict the domain. These x values will be the location of either a vertical asymptote or a hole in the graph. So, looking down here, a hole occurs when the factor in the denominator cancels out with the factors in the numerator. A vertical asymptote occurs when a factor in the denominator cannot cancel with the factors in the numerator. So it's important to remember, just like yesterday when we were doing zeros, zeros always came from the numerator, right? We always looked at the numerator. We only looked at the denominator to rule out a zero that might also be a discontinuity. So vertical asymptotes and holes are going to be the opposites. They always come from the denominator. So your holes or vertical asymptotes always come from the denominator. You need to look at the numerator to decide if it is a hole or a vertical asymptote, but they always come from the denominator. So, for example, the functions f and g both have a hole at x equals 1. I don't think that's the graph of, I don't know which one that's the graph of. I think this is just a graph example here. So a function that has a hole, the ones that you guys saw in math, the ones that you saw in math 3 looked like this first example. Because right here, that x minus 1 and x minus 1 would cancel. That would mean that x equals 1, you have a hole in the graph. Look at this second example. It's a little bit different. I've got x minus 1 to the third and x minus 1 to the second. So if we want to think about what that looks like, that is x minus 1 times x minus 1 times x minus 1 over x minus 1 times x minus 1, and then you also have that 2 right there. So in this case, these cancel and these cancel. So all of our x minus 1's in the denominator canceled. So that is going to be a hole in the graph, right? Pretty much if your exponent on bottom is smaller than the one on top, then you end up with a hole at that point. But we're going to see something else happen over here. Holes are just going to be shown by a open circle right here. You have to be really careful on Desmos for these, because if I pull up Desmos real quick and I type in something that has a hole equals x plus 1, x minus 2 over x plus 1. Do you guys see the hole at negative 1? It's not there, right? It doesn't show up. That is because negative 1's not on the graph, but negative 0.999999999 is. So theoretically, the hole doesn't show up whenever you're looking at it. The only way you can tell on Desmos is if you take your cursor and click on it and drag it across. If you can get it to go right at negative 1, it'll turn to a hole and tell you that it's undefined at that point. But that is not very easy to see when you're looking at the graph, and it's a little difficult. It's very difficult to find if you're just like going up and down like this right here. If you know you're looking at negative 1, then it makes it a little bit easier to see. Most of these are going to be calculator inactive anyway, but I wanted to point that out in case you're checking anything with Desmos there. Okay, vertical asymptotes are going to be the lines that we get closer and closer and closer and closer to. They look like this right here where we approach a value. So this graph also has a vertical asymptote right here, but it has a hole at this point. This graph has a vertical asymptote at x equals 1. You're going to see vertical asymptotes whenever you have a 0 in the denominator that does not cancel. So you can see here, this is what we would look at in Math 3. That x minus 1 does not cancel with anything in the top. So you're going to have a vertical asymptote at x equals 1. G of x is a little bit different because we got x minus 1, x plus 2, and x minus 1 squared. You do have an x minus 1 that will cancel, but here's what's happening there. You got x minus 1. Oh, gosh. Why does it do this? Let me try writing it up here. X minus 1 times x plus 2 over x minus 1 times x minus 1. So this set cancels, but you still have an x minus 1 left in the denominator. So what happens is you've got like a whole and an asymptote at that point, but if that ever occurs, an asymptote sort of trumps a whole, right? It's more important. So you can't have both at the same spot. If you have a whole and an asymptote, it's just an asymptote for that. And that's what's going on right here on that second.
So if the factor's left on the bottom, it's an asymptote, but then if it cancels and there's no factor left on the bottom, it's a whole?
Correct.
Okay.
What if there are two left on the bottom?
You can have more than one vertical asymptote. So technically you could have infinite. So like as far as the graph goes, that would look, let me put this up here. Like if I had this just has a hole, but let's say there was a x minus 3 and x plus 5 here. You'll get two places where you got those vertical asymptotes. So, and there could be 3 or 4 or 5. It's just that gets pretty complicated. We're not going to see it as often. There. Okay. Now, they do have us doing a little bit of limit notation here. Okay. So, at a limit, or at a whole, your limit is going to approach a certain value. Okay? So, whenever they tell you, this is some new terminology that we've got here, and I don't think he goes through it later. I feel like I might should just like add some limit terminology in before I do this, but we'll figure it out now. So, when you see limit as x approaches 1, and you got this little negative behind the 1. Okay? So if you have the negative behind the 1, that means as x approaches 1 from the left. We call it a one-sided limit. You're only looking at the left side. So what you're doing whenever you're talking about the limit here is that you are thinking about tracing that graph up here from the left side. Oh, it's not even going to let me. I'm just going to have to use the pointer because it's going to do crazy stuff. But if I think about tracing this graph from the left side as I get closer and closer and closer to where x equals 1, then I'm thinking about what happens to my y value. At 1, the function is not 3 because there's a hole in that graph. But if you think about what you're getting closer and closer and closer to, I'm going to that point, I just don't ever get there, right? So a limit doesn't have to be like a place where you have a closed circle. You are approaching 3 for that. So the limit as x approaches 1 from the left of f of x equals 3. So as you get closer and closer and closer to x equaling 1, your y coordinate gets closer and closer to being 3. This notation right here, where we've got limit as x approaches 1, and there's a positive after it, not before, that is telling us from the right. At a whole, you should have your left and your right should be meeting at one point where you've got an open circle right there. And the limit that you give is just the y coordinate of that point. At vertical asymptotes, if we look at limit notation, x equals 1 is the vertical asymptote that we see right here on this graph. So if we're looking at the limit as x approaches 1 from the left of f of x, that's what's happening to your y values as you get closer and closer and closer to 1. And from the left side, what happens? You go down forever, right? So that's negative infinity. But from the right side, you're going to approach positive infinity for that.
So is that, so with the hole, like from the left side, it's the left side with the hole, not this like left.
Right. These limits are asking us to approach 1. So 1 happens, I don't know if it'll let me draw on this very well because it's a table, but 1 is right here. So for this one, we are looking at the point where x equals 1. There is also a vertical asymptote over here, so if we were talking about negative 1, we'd have different answers for that. But right here, they're talking about 1. Over here, we're also talking about 1, but our graph is different. That's where we've got a vertical asymptote. Okay, questions? Okay, so we're going to have things like this, and we're going to be asked to find any holes or vertical asymptotes. So, what I like to do when I'm doing this problem, look at that denominator first. You definitely have discontinuities, either holes or asymptotes, at x equals negative 3 and x equals 5. Whether they cancel or not, they're discontinuities. So you have discontinuities here. But specifically, we want to know which type of discontinuity we have. So the x plus 3 cancels, so that one is going to be a hole. The 5 does not cancel, so that's a vertical asymptote. For B, we've got x minus 2 and x plus 1 in the denominator. So definitely I have discontinuities at x equals 2 and x equals negative 1. Okay, so either one of those numbers gives me a 0 in the denominator. To know if it's a whole, I'm going to write this one out the long way. You can think about it. You don't have to write it, but this is x plus 1, x minus 2, x minus 2. On the bottom, you would have x minus 2, x plus 1, x plus 1. So if we look at what will cancel here, I got an x minus 2 that cancels with the x minus 2 in the top. I've got an x plus 1 that cancels with the x plus 1 in the bottom. So is 2 going to be a whole or a asymptote? That one is a whole because you don't have any more of them left in the bottom, right? But what about negative 1?
Is that vertical because there's still 1?
There's still an x plus 1 left in the denominator, so that's going to be a vertical asymptote. I don't mind you shortcutting that to VA on like your homework and stuff. Probably don't do it on a test, or definitely not the AP exam. They have to all cancel for it. Yeah, all the ones on the bottom have to cancel for it to be a whole. So what you have is you got like a whole and a vertical asymptote at the same time, and that can't happen. The vertical asymptote wins out for that. All right. C is not factored, so we want to factor that if we can. What could we do to factor that one? Take out an x, so that'll leave us with x squared plus 4. Will that factor any further? No, that would be x squared minus 4. The plus 4 won't work because if you did like x plus 2 times x plus 2, it'd give you a 4x in the middle. You'd have x squared plus 4x plus 4, which is not what we're looking for. So that one does not factor. So when I'm doing discontinuities for C, here, this x right here is going to give me an x equals 0. What number would make x squared plus 4 0? Let's like solve it out. X squared plus 4 equals 0. I would subtract my 4. So x squared would equal -4. Then what would I have to do? Right? What do I get? I get plus or minus 2i. Is that a real number? That you can't have vertical asymptotes at imaginary numbers because they don't. Nothing imaginary shows up on the graph. This tells you you got nothing. Here you're not going to have a vertical asymptote or a hole at that point. So 0 is your only discontinuity for this. And is 0 going to be a vertical asymptote or a hole? Vertical asymptote. There's nothing for it to cancel with in the top, so it's vertical asymptote. So you would just have that 1 for that problem. If you think about x squared plus 4, it should make sense that that can't equal 0 because when you square a number, what kind of number do you get? Positive. Always positive. And if you add 4 more to it, it's even more positive than it was to begin with, right? So there's no way that can equal 0. So that's what happens there.
Can you have a whole term as like x to the 3 plus 4x? Should that be an entire vertical asymptote if it was, or no? Do you just have like a set number, or do you have a term as?
You would, if you have a term, we'd have to do like we did with x squared plus 4 and set that equal to 0 and find where those numbers are, which does not always result in not getting anything at all, but will a lot of times be the case. All right, so we are supposed to write a left and right limits statement as x approaches 2 for each of the following functions. Okay, so for this, for f of x equals x minus 1, x plus 3, x over 2. At x equals 2, do we have a vertical asymptote or a hole? Vertical asymptote, because that does not cancel with what's in the numerator. So, what's the best way to do this without a calculator? Probably sign chart, I think. Either sign chart or making like a table for that. Probably sign chart is going to be easier because what we should know here is my left limit, and this is not talking about left and right end behavior. It's not asking about end behavior here. It's asking about what is happening at 2. Right, so pretty much I want to know if my vertical asymptote goes like this, or like this, or you could have them both go up, or you could have them both go down. Right, that's what they're asking us here. So we could graph it and see it. That's one way, but that's not always available for us. So if I'm doing x approaches 2 from the left of f of x, then I want to know what's happening right there at 2. I think our best bet is going to be to do a sign chart like we did for the increase or for the inequalities, because if we do that, our zeros will be 1, -3, and 2. So we got -3, 1, 2. We've got x minus 1, x plus 3, x minus 2, and the answer, you really only care right there at 2 if you want to leave some of it off, but I think it's just easier for me to do the whole thing. like this. So I've just filled that in really quickly. Notice it switches from negative to positive at 1 for that top line, at -3 for the middle line, at 2 for the bottom line. That sort of always happens. That's why, like, as you become more comfortable with the chart, that's why it's much quicker than other methods. So that answer is negative, positive, negative, positive. In this case, they're only asking us about, like, right here at 2. On the left side, what's your function?
Oh, wait. No.
It's negative right here. Like, now it goes negative, positive, negative, but we care about, like, what's happening as we get closest, right? So we're getting a negative here. So that would be negative infinity.
So
right?
It's just like the place right beside.
Right. So I'm only looking, like, right here beside 2. Right? That's where I'm getting my negative infinity. And then so on the right side, my limit as x approaches 2 from the right of f of x would be positive infinity. And I'm getting that right here from that part of the sign chart. Yes?
So it's like, say the right side, if it's negative, it would be approaching negative.
Correct. Correct. And you can have any combination. Like, you can have both of them going down, both of them going up. You can have them going opposite directions for that. So you're just looking at, right there at 2 where you have vertical asymptote, you're looking at your signs that you have on the left and the right side. So really, if I wanted to leave off -3 and 1 altogether because they're not my vertical asymptotes, I could. I just think it's easier to make the whole chart and see where you would fill things in. But you're only looking right there at 2 for this problem. Okay. Questions on that? All right. 4B. This question is only asking us about at 2. So at x equals 2, what do I have for this graph? It's a hole because these 2 right here cancel. I do have a vertical asymptote at 3, but they did not ask me about 3, so I don't have to consider it for this problem. So whenever I do this problem, the limit as x approaches 2 from the left of f of x, and the limit as x approaches 2 from the right of f of x. Those 2 limits should be equal to the same thing, because if you have a hole in the graph, that just means like this side goes here and this side goes here, but you just have an open circle, right? So you should get the same number here. The number that you are going to get is what you would get if you plugged 2 into the simplified equation, okay? So, like, if I plug 2 in to this equation, I would get 0 over 0, which is an indeterminate form, and that is not a real answer. But if I cancel these out and I plug in 2, I would have 2 plus 4 over 2 minus 3, which would be 6 over -1. Give me -6. So -6 will be your answer for both of those. It feels wrong to teach you this without teaching you more about limits, but that is what you do.
So with vertical asymptotes, you use the sign chart, and then with holes, you just plug
Yeah.
what the hole is in.
Right. Right. Another option for this is, like, you could plug in numbers that approach 2. If you plug in 2, you're going to get a number over 0. So another option is you could plug in like 1, 1.5, 1.9, 1.99. It's not usually very easy to do unless you, it's not very easy to do unless you have a calculator though. So I would generally go sign chart on that. Okay? For this last one, I've got x minus 4x minus 2 over x minus 2 squared. So for this one, at x equals 2, do I have a whole or a vertical asymptote? Only one is going to cancel. So like if you canceled it, this would cancel and you'd have one that was left in the bottom, right? So this is going to be a vertical asymptote for this one as well. There would be 2 vertical asymptotes, so x equals 1 would also be a vertical asymptote. We don't have to do limit statements for that because it's not asking for those, but you would also have a vertical asymptote there as well. So if we do a sign chart for this one, if you're going to get a vertical asymptote, you need to do a sign chart. So we've got 4, 2, and 1. So let's put those on the number line. We got 1, 2, 4. You need to put every piece, even if it cancels out. So you need to think about like the original graph. Don't use the canceled out version. So you got x minus 4, x minus 2, x minus 2 squared, and x minus 1, and then the answer. I'm about to run out of room down there at the bottom. Now for this one, for that middle line right there, x minus 2 squared, what will you get all the way across for that one? That one's positives, because when you square something, it is positive. And then for the others, you're going to get negative, 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 positive, negative, negative, positive, positive here, and negative, positive, positive, positive. So on that answer line, you'll get negative, positive, negative, positive. And we are looking here at 2 because the question wanted us to ask about 2. You could also look at 1 if they wanted you to, but they asked us for 2 here. So for the left, our limit as x approaches 2 from the left of, actually this is h of x. Oh, and that one was g. I really should be more careful with that because if you have a problem, like a couple of you did this on the test, on that very last question where you had like h plus x and you had to do the in behavior, you used the f of x, which I let slide because there was no other f of x in that problem. But if there had been an f of x, it would not be good. So try to use the letter that they are actually using. So h of x, we would get for the left side, what are we going to get? We'll get positive infinity because as we approach 2 from the left, I've got positives right here. And then for the right side, which I just about don't have room for, limit as x approaches 2 from the right of h of x would equal negative infinity. And we get that from looking at the left side there. Okay, questions? All right. 3, this is kind of a tricky problem right here. It says write an equation of a rational function with the following limit properties. Okay, so I've got the limit as x approaches 3 from the left of f of x equals 5, and the limit from that right approaches as we approach 3 from the right equals 5. What do I have at that point? A whole at x equals 3. So when I'm thinking about writing this equation, if I have a whole at x equals 3, I have got to have an x minus 3 on top and an x minus 3 on bottom so that they will cancel each other out. If I wanted to be more complicated and put like squares or something in there, I could, but I would just go bare minimum on this.
Do you need to do anything with 5 or no?
We are going to need to do something with 5. So we're not done with that information, but the 5 is important here. For my 1, x approaches 1 from the left and x approaches 1 from the right. What have I got at that point? Vertical asymptote, right? So vertical asymptote at x equals 1. So that means I need an x minus 1 in the denominator that does not cancel out. Okay, so you got a couple things you have to think about. You have to think about if your vertical asymptote would both go in the negative, positive direction here. You also need to get a 5 whenever you're looking at the whole. So whenever we did the whole up here, I canceled out my 2's and I plugged the number into what was left, right? So if we think about that at 3, okay, if I am going to cancel out my whole and I'm going to plug in a 3 right here, then in the bottom of that fraction, I'm going to get a 3 minus 1, which will equal a 2. Now, right now, as it is, I would just have a 1 in the top, and I would get 1/2. That is not what I want for my answer. I want to get a 10 in the top so I can get a 5, right? The easiest way to do that is to just put a 10 right here. Another way you could do that, instead, if you wanted to, you could do something like x minus, or x plus 7 would work, because 3 plus 7 would give you 10 there. That would also work. There's several options that you could have for this. So I'm going to, actually, the very easiest way right here is just to do the 10 for that. Because if you do that, then your asymptote should be negative on the left, positive on the right. For that, if you were to make a chart for that. Because I said you need to include all the pieces, but actually if they cancel, you could leave them off, because they're going to, like, if you have a negative and a negative, it makes a positive there. So, and they're going to be the same. So if I left this off, if I was making a sign chart, the top would be 10, that'd be all positives, right? If I made a sign chart where I only cared about my vertical asymptote, I would just care about 1. And I would only care about the 10 and the x minus 1. The 10 is already positive all the way across. The 1 would be negative here, positive here, so you get negative, positive for your answer, which is what we want in this case. So this would be the easiest way right here. Let me get rid of my canceling this out. Right here. Okay, so that's what I would do. There could be other possibilities. Let's leave it like that. Okay, questions? Yes. You can go after, yeah. As long as you're just still multiplying, that'd be fine. Okay, for B, we have got a whole at x equals -2, and we're going to have a vertical asymptote at x equals -1. So for this function, we definitely need to have an x plus 2 in the top and the bottom. That'll take care of our whole. We also need to have an x plus 1 in the bottom to get a vertical asymptote. So let's think about this 4 right here first. So right now, x plus 2 will cancel. If they do cancel, then I'm having to plug in, what I'm doing is I'm doing like the limit as x approaches 2. I'm having to plug, there's just a 1 in the top, and I'm having to plug in a 2 plus 1 here, so I get 1 over 3. I don't want 3. What am I trying to get? I'm trying to get 4, which means I need a 12 in the top. So to fix this, I can put a 12 up here in the top. Or you could put an x plus 10. That would work also. Mm-hmm. Oh, have I done it backwards? I should do the -2. You were right. Okay, no 12. I did it right on the last one, though, didn't I? Yeah, I approached through there. Okay, yes, it should be a -2. I should use what the limit is approaching, not what the factor is. So you need to use the 0. I did it correctly over here because I was plugging in a +3 for that. I should do a -2 for this one, so I messed that one up. Thank you for catching that, Molly. Yeah, because that I wouldn't have ever thought I taught you that one wrong. So that means you're getting a -1 in the bottom. If you are getting a -1 in the bottom, then you need to have a -4 in the top. So you could put a -4 up here. Oh gosh, no, this one gets super complicated. Because you need your vertical asymptote to be positive. Which means I think you need to square this. But then the negative makes it go negative. I don't think you have one quite this bad. I don't remember doing this year. This must have been one last year I ran out of time and didn't do. I don't remember doing it last year. Okay, let's think that. Let's go back. Okay. Maybe we should think about a vertical asymptote first. Let's try again. It still ain't gonna work. I'm not gonna give you one this hard. Maybe one like A. Not like B. We just don't have time to do it. We could figure it out, but I just don't think it's worth our time. I think I may confuse you more than it's gonna help. So sketch a picture of a rational function that has the following properties. F has a hole at x equals 1. As x approaches 4 from the left, f increases without bound. As x approaches 4 from the right, f of x decreases without bound. So whenever we sketch a graph here, this is a lot easier than what we were doing before. We got 1, 2, 3, 4. 1, 2, 3, 4. I am not going to put y. I'm not going to label my y-axis because it doesn't give us any y coordinates that we need to worry about. I'm going to have a vertical asymptote at 4. So I'm going to put myself a dotted line right here. It's not actually part of our graph. It is just there to guide me for my vertical asymptote. So as x approaches 4 from the left, f increases without bound. So from the left side, I'm just going to do this. I know that I got to go up right here. And it tells us as x approaches 4 from the right, f of x decreases without bound. So as I go to the right of this, I should go down. It really does not matter what the rest of this graph does. You can make it look however you want. The only thing that matters, so I mean I could do anything I want here with this graph. I could do that. It probably doesn't actually do that, but I could. The only thing that is important is that wherever I draw that line, I got to go back to 0, or back to where x equals 1. Oh shoot, it erased the whole thing. So I had this, and I've got to erase a little bit, and I got to put an open circle right there. And I'll put the arrow over here on the end too. What's more likely to happen is you'll have like a horizontal asymptote there, but it technically could do anything crazy there. For B, we're going to have holes at -2 and 3, and then we've got an asymptote at -1. So if we graph our axis here, we got 1, 2, 3, 1, 2, 3, and our vertical asymptote is at -1. So I would draw in the asymptote part first. As x approaches -1, from the left, g of x decreases without bound. So it's going to go down like this on the left side. As x approaches -1 from the right, g of x decreases without bound. So the left side also goes down. Then, it does not let me erase very well here. I would go to x equals -2, and wherever the graph is, you want to put an open circle right there. I'm going to kind of do that because it doesn't let me erase very well. You guys can erase. And then x equals 3. I'm going to go over here to where x equals 3, and I'm going to put me an open circle right there at that point also. It took me longer than I wanted to because of that problem. I need